This absorption compression heat pump works because it integrates an electric mechanical compressor directly into a thermal fluid absorption loop. The clever bit here is driving simultaneous thermal and electrical energy inputs. Standard industrial heating systems rely strictly on either high-voltage grid power or direct fuel combustion, limiting their overall operational efficiency and adaptability. By merging mechanical vapor compression with liquid absorption cycles into one hybrid network, overall energy performance expands far beyond standard single technology limits. This hybrid device delivers versatile heating and cooling effects by taking full advantage of both thermal and electrical energy sources simultaneously. However, relying solely on standard mechanical vapor compression at high industrial temperatures require massive electrical power inputs that severely inflate operational energy bills. Conversely, conventional liquid absorption heat pumps struggle significantly when driven by low-grade waste heat, failing to reach the elevated temperatures required for process steam. Operating either technology in isolation leaves industrial facilities facing narrow working temperature ranges, excessive utility expenses, and large quantities of unrecovered thermal waste. This fundamental conflict between heavy electrical demand and restricted thermal performance hampered deep energy recovery efforts across energy-intensive processing industries. Engineers resolved this performance limitation by installing an electrically driven mechanical compressor directly into the circulating solution loop of the absorption heat pump. This integrated electric compressor elevates internal refrigerant vapor pressures, enabling low-temperature thermal waste streams to activate the absorption cycle efficiently. By sharing the thermodynamic workload between mechanical power and solution absorption, the hybrid cycle dramatically cuts expensive high-voltage electricity consumption. The unified absorption compression architecture provides extraordinary operating flexibility, seamlessly balancing thermal and electrical inputs to match dynamic industrial production requirements. The bigger problem is upgrading low-quality industrial waste heat into high-grade process heat without consuming huge amounts of primary fuel or grid electricity. Industrial processing plants reject immense quantities of low-temperature thermal exhaust and liquid effluent that conventional recovery systems cannot economically elevate to useful steam temperatures. Upgrading this low-grade thermal waste requires a sophisticated thermodynamic mechanism capable of dramatically raising temperature quality while keeping operating costs exceptionally low. Bridging this massive thermal gap efficiently seemed thermodynamically impractical using standalone equipment without incurring prohibitive electrical expenses or massive capital costs.
The core methodology relies on closely coupling the absorption compression heat pump with an on-site industrial cogeneration plant that generates both electricity and useful heat. The cogeneration system combusts fuel to generate electrical power while producing high-grade thermal exhaust, creating an ideal dual-energy foundation for the hybrid system. Electrical power generated by the cogeneration unit drives the electric compressor, mechanically boosting refrigerant vapor inside the hybrid heat pump assembly. Simultaneously, thermal energy harvested from the cogeneration exhaust feeds directly into the solution generator of the absorption heat pump circuit. Inside the absorber, a liquid working fluid mixture absorbs refrigerant vapor, releasing useful heat at a medium temperature as the vapor dissolves into solution. A solution pump then transfers the liquid absorbent mixture to the generator, increasing liquid pressure while consuming only a minimal amount of pump power. In the solution generator, driving heat boils off the refrigerant vapor, separating it from the absorbent solution under high operating pressure conditions. Instead of relying purely on high driving temperatures to boil off refrigerant, the electric compressor mechanically boosts the refrigerant vapor pressure. This mechanical pressure boost lowers the required generator driving temperature, allowing low-grade industrial waste heat to drive the fluid separation process. The high-pressure refrigerant vapor flows into the condenser, releasing elevated high-temperature thermal energy directly to the factory process water loop. After condensing into a high-pressure liquid, the refrigerant flows through an expansion valve, dropping its pressure and temperature before entering the evaporator. In the evaporator, low-temperature industrial waste heat boils the cold refrigerant liquid back into vapor, effectively absorbing waste thermal energy from process exhaust. The low-pressure refrigerant vapor returns to the absorber, where it dissolves into the liquid solution, completing the continuous closed thermodynamic cycle. By simultaneously manipulating internal pressure with the electric compressor and liquid concentration with the absorption mixture, total temperature lift is dramatically multiplied. This dual pressure and concentration control enables the system to boost low-grade waste heat up to high-value industrial process steam temperatures. Facility managers can reconfigure operational parameters to optimize output for maximum cooling, high-temperature heating, or combined multi-thermal delivery depending on facility demand. When configured specifically for thermal upgrading, the integrated system maximizes high-temperature heat production production from a fixed amount of consumed fuel. Improving the temperature quality of industrial waste heat represents the most heavily researched and commercially effective application of absorption compression heat pump technology.
Integrating mechanical compression with fluid absorption yields performance coefficients far superior to those achieved by standard vapor compression or absorption cycles alone. This thermodynamic synergy forms an efficient, high-performance link that transforms unusable low-grade thermal waste into valuable industrial process energy. By uniting electrical vapor compression with thermal liquid absorption, engineering transforms low-temperature industrial waste heat into valuable high-grade thermal energy. This hybrid integration enables cogeneration systems to maximize total primary fuel efficiency while delivering flexible, high-temperature heating and cooling outputs. Mechanical compression integration overcomes the thermodynamic limitations of traditional thermal absorption loops operating on low-grade industrial waste heat streams. At the same time, liquid absorption technology cuts the heavy electrical energy consumption typically required by pure mechanical compression systems. This hybrid absorption compression framework offers a flexible, robust solution for industrial thermal decarbonization and heavy-duty waste heat recovery. The absorption compression heat pump proves that combining mechanical and thermal thermodynamic mechanisms unlocks maximum efficiency in modern industrial thermal management.